Okay, so yeah, hi everyone. I'm happy to introduce you Markus Michael Rao today, who will be giving a talk. He is currently a postdoc at the Argonne National Labs in Chicago, and before that he did his first postdoc with Rachel Mandelbaum back at the CMU in Pittsburgh, and before that he did his PhD in Munich, and he specifically focuses on developing statistical methods to estimate photometrical redshift distributions for various galactic surveys, cosmological surveys. And I think in the first place, he applied it to the dark energy survey, for example, and now you've switched more to the Rubin Observatory. And I think during your talk, you'll be talking about specifically what you've been up to during your postdoc in Argonne.
Thank you so much, Christina. Yes, so let me maybe share my screen. Okay. So thank you so much for giving me the opportunity to talk about my work. So as Christina already said, I'm a postdoc at Argonne. I will talk about today about cosmological inference and photometric surveys under redshift uncertainty. When I say cosmological inference, I want to make that clear in the beginning. I mainly talk about inferences that use two-point statistics, so 3x2 weak lensing LSS type of probes. We had a recent paper on the HSC survey, so I'm very involved in the HSC survey, which is a stage 3 survey. And at the moment, I'm also the lead of the Photometric working group in LSST as we prepare for first data. So I will talk about both of these aspects in this talk. I'll give you a little bit of an overview about what we will talk about today. So I will highlight and try to give you an overview about challenges in photometric redshift estimation and how it relates to cosmological inference. And I will mainly use as an example the year 3 analysis that I've led on the Suprime-Cam survey, which is a precursor survey to LSST, but quite similar in its survey specifications. And then I will talk about a little bit more technical aspects. I will highlight that what we are talking here about today can be phrased as an inverse problem. And it has a lot of, I think, interesting implications for the methodology. I will highlight the HSC Photometric analysis methodology that I've been using for the year 3 survey, and highlight a couple of results and conclusions and avenues for future work. So let's dig into the data. So the main survey that we will talk about today is the HSC survey that is a broadband photometric survey in GRIZY, which is the filter bands are shown here on the left. So broadband photometric survey. On the right-hand side, you see how it relates to other surveys that are also optical imaging surveys. And you see that HSC in general, in comparison to, for example, KITS, that's also shown here, or DES, which are all these stage 3 surveys that are currently putting out a cosmological results, has typically smaller areas. So it's a smaller area survey, but it's quite deep. So that's the characteristic survey strategy that HSC has been adopting. And if you, for instance, compare HSC wide, on the x-axis here on the right-hand side, you see area. On the y-axis, you see the depth in the main detection band. If you compare, for example, HSC wide with LSST, you see it's maybe a magnitude shallower, but it's quite similar in terms of depth. And that's quite interesting for us as people who work on statistical methodology, because depth is what's really challenging in these kinds of scenarios, because it relates more to systematics. Whereas area, if you increase the area of an optical imaging survey, you decrease the statistical uncertainty, but that's typically easier to parameterize. The concrete data that we will talk about today is HSC in its year 3 stage. So we have 470 square degrees area, and we go to a magnitude of of 24.5 in I-band. The HSC strategic program is a wide field imaging survey with 1.77 square degrees field of view at an 8.2 meter Subaru telescope. And we will talk about a tomographic redshift analysis, which means that we will split the survey in bins of increasing redshift to maximize essentially our information on the growth function in a cosmological analysis. So let's talk a little bit about this particular statistical problem that we will talk about today, which is what we want to talk about today is how to estimate the distance or redshift of galaxies in these kinds of surveys, and how that relates to cosmological inference. So, of course, imaging surveys take pictures of galaxies. So in order to construct theory predictions for things like two-point functions, we actually need to reconstruct, what is our line of sight distribution of galaxies, because that enters essentially this theory prediction as a projection kernel. And it has been clear from previous years of HSC analysis that the uncertainty in estimating these kinds of redshifts for galaxies, so these distance estimates, is one of the dominant sources of systematic. And so, for example, what I show you here on the left-hand panel is a sensitivity study in the Y1 HSC analysis. So you see here on the x-axis the S8 constraints. S8 is a constructed cosmological parameter of sigma 8 and omega meta, and alongside the characteristic recleansing degeneracy plane. And what you see here is essentially how much this S8 constraint changes when you modify your assumptions. It's not super important which assumptions these are, but I want to show you two dominant sources of systematic. So, for instance, you see AB varied is one of the components that affect the constraints quite a lot, and this is related to the intrinsic alignment amplitude. And the other factor that affects these constraints very much is in the lower part of this list, which are PZ related quantities, and PZ often refers to photometric redshift codes. So when you essentially change your photometric redshift methodology, you have quite a big effect on these constraints. And on the right-hand side,
Markus, quick question. So what sort of changes are you talking about for this methodologies? I mean, what's the thing that's changing?
Yeah, so the thing that's changing is, for example, the modeling of the spectral energy distributions. That's one of the things that will change. Whether you use a machine learning code that relies on training sets, or whether you use a forward modeling approach. So these kinds of fundamental analysis assumptions can also change. So I will talk about the different methodologies during this talk, but you're talking about just modifications in your modeling of your photometry and SCTs. Exactly. So and on the right hand side, what I show you here is essentially what forecast of the impact of different methodologies on the year 3 results, because year 3 has an increase of area, so the statistical uncertainty will shrink, so systematics become more abundant. And just to highlight the importance of being careful about photometric redshifts, what you see here is omega meta against sigma 8. So these are again two cosmological parameters, and you see half a sigma shift approximately in this S8 dimension. Again, when we change from the Y1 methodology to the Y3 methodology. So half a sigma shift doesn't seem extremely much. Yeah, so it's not something that would worry you a priori. But if you think about that, we have here 420 square degrees in an HSC survey, and we are looking towards LSST. Yeah, and LSST will have over 10,000 square degrees. So you're looking at orders of magnitude larger area. And these kinds of systematics are absolutely unacceptable, and they will dominate the error budget. So this is just to to give you an example of how important these kinds of systematics are at the moment. They really are important for getting our cosmology right. So let me give you an overview about the photometric redshift problem, why it's so difficult, and also what can be learned even if you are not working in survey science from this kind of problem. So what I show you here is on the left-hand side a basic setup that we want to analyze. So we want to obtain the line of sight distribution of galaxies from the redshift measurements of individual galaxies. So how do you measure a redshift in the context of photometric surveys? And this is shown on the lower right panel. So assume you have GRI-ZY, so these are these filter bands, and you perform measurements of the SED of a galaxy in these filter bands. So essentially you get points of GRI-ZY. So what you can do is you can model the SED of the galaxy, and you can redshift it through these filter bands. And then you compare the redshifted model SED with your measurement, and that gives you information about the redshift of the object. So as I said, so these are optical imaging surveys. So you have GRI-YZ, so you have only information, broadband information in the optical. You know, everything is fine if you have a red galaxy, for example. Red galaxies have a very characteristic spectral energy distribution. This is shown in the top panel here. So you have the 4000 angstrom break that just shifts through these optical filter bands. It's relatively easy to get a redshift for them. But let's, but this galaxy data contains other types of galaxies, for example, SBC galaxies. And the issue that you have with these optical imaging surveys is you can have an SBC galaxy sitting at a redshift of 0.5 and an elliptical galaxy sitting at 0.3, and they have very similar responses in optics, in the optical filter bands. This is really difficult because this relates to a statistical concept called lack of identifiability. So you can have 2 points in parameter space. Parameter space here means morphology against redshift, and they will produce very similar theory predictions. Yeah, so it's very difficult to disentangle these two models. And this has severe complications for our redshift inference. And this is shown here in the left-hand panel. So what we would do is we would evaluate essentially likelihoods for all our galaxies using that kind of setup. And what you would get are these 3 distributions or likelihood functions in this case, which I illustrate here in the left-hand plot here. So you see a red one, a blue one, and a green one. And I'll show you 3 different cases that you can encounter. So the red one has multiple peaks, is very broad. Yeah, so you're looking at essentially you do not really know where the galaxy sits because you have these multiple double solutions essentially. Yeah, so it's really a galaxy where you would not know exactly at which redshift it is. You have the blue case, which is somewhat constrained, but you still have these double peaks, and you can have galaxy types like in this case green that is very, very constrained. And so what this just illustrates is that you have a very complex error model for these galaxies. Now your task now in the context of optical surveys is you need to infer what is the sample redshift distribution, so the line of sight density of galaxies given this kind of error model. This is a classical deconvolution problem. Yeah, so you need to essentially deconvolve the distribution of the full sample, the redshift distribution of the full sample, given these error models. And that is extremely difficult if you have these lack of identifiability problems. So what I show you here is essentially you have 2 different types of information that you can use to perform this deconvolution of the sample redshift distribution with respect to these error models. The first one is, of course, the photometry, and we talked about this in the lower right panel. So it's classical SED fitting approaches. But you also have, of course, additional information from the spatial distribution of galaxies. Yeah, because of course structure structure evolves with or clusters with Redshift. So you can perform 2-point statistics that give you additional information of the sample Redshift distribution. And of course, the goal is to get something that's shown on the right-hand side, and I will explain this plot in the coming presentation, where you see you have very clean tomographic bins and a consistency between different types of constraints. So to summarize, and that's very important, you have these challenges of the mapping between photometry and parameter space, meaning Redshift and template space being ill-conditioned. You can have multiple solutions, and you can have also issues with your calibration of these kinds of mappings. So because spectra are very difficult to obtain at these faint for these faint galaxy samples. So just to give you a little bit of an illustration here. So this is the part of a broader class. It's called inverse problems. So inverse problems have often, and I grossly oversimplify this, a structure that I show you here. So you have an error model, so P error. You have a true spectrum or true distribution. This is on the right-hand side, P of C, and you have an instrument response typically, which is on the left-hand side, P noisy. So you smear out an original distribution or spectrum with respect to an error model, and you get a noisy measurement. So this is illustrated in the top panel. So what I show you here is due to the Redshift error that can be quite broad, you're smearing out essentially a line of sight distribution of galaxies, and this is shown here with these gray error bands, which would illustrate essentially your measurement of the smeared out distribution. And what you want to do is you want to deconvolve with respect to the error model to get the black dashed distribution that is much narrower because it is not convolved with an error model. So in order to if you solve this kind of inverse problem with respect to your error model, you can sometimes have the issue that your variance in your parameter space blows up. And this is shown here on the right-hand side. So each draw of the right-hand side is consistent with the gray error bands. Right? And the noise that I impose is here illustrated using this horizontal bar, so 1 sigma noise. So you would have an error model that is this wide, and this leads to the smearing out effect that blows up your parameter space. And if you calculate this using basic linear algebra, one can very easily see why this is the case. Let's discretize this integral equation here into P noisy, K error, and P true. So this is all discretized on the grid, where K error is essentially an operator or a matrix. You would you try to get to recover P true. You invert K error, and what you see here is you can decompose P true using eigenvectors and of K error and eigenvalues of the K error matrix. And the issue that you have is that this eigenvalue. Yes, please go ahead.
So just so that I understand the goal. You're not interested in the estimating the redshift of a particular galaxy, but only for the distribution. Okay. Mm-hmm. So I was just wondering. I mean, this entire process is something that we in X-ray spectral analysis or encounter a lot, right? I mean, your error distribution is a lot like an RMF, and you have where again, I mean, you have several spectral models which map to the same kind of observed PHA distributions. I'm just wondering if there is something there that you can, I mean, there's a huge machinery built up to do forward modeling in those cases. And I was wondering if there is something that that could translate here, but you don't have to answer that right now. I'm just speculating.
No, I think there are, I mean, these kinds of problems appear a lot, right? So for example, even if you look at particle physics, like pattern distribution function modeling, classical example, is an absolute inverse problem because it becomes more and more complicated if for example, if you if your distribution that you would like to model has a lot of parameters, because that often makes it difficult. But there are a lot of, I think there are a lot of commonalities that one could explore and see, you know, what if that helps, especially in terms of regularization. So how do you regularize the problem to beat down this noise, for example? Yeah, I think that's yeah.
Okay. Thank you.
Yeah, but I mean, if you are an expert in this, I mean, as I said, so you know the basic problem is that the conditioning of this mapping is just not very good. It can be difficult, and you have this increase in variance, and because the eigenvector here is in the denominator, and if that is
yeah, I mean this is also similar to the line intensity to emission measure distribution temperature, that problem that we usually encounter in stellar physics. Christina would know more about that.
Yeah.
Yeah, yeah, you're right. It is. It's a common problem.
It's a very common problem. Yeah. All right. So so we designed the HSC analysis strategy basically around that problem to try to eliminate as much issues that we have. So first of all, if you have this lack of identifiability problems in your SED fits, you can these deconvolutions become very difficult. So we try to optimize our sample selection, so essentially cutting out data that's problematic. We also have a model combination scheme that averages over several different approaches to do for example, SED fitting and SED modeling. And we include a complementary data. In this case, we exploit you know, spatial cross correlations as an additional calibration. And at the end of the day, we are very aware that there are still residual systematics in our analysis. So we try to construct a very conservative error budget. I can quickly go over the next couple of slides. So in terms of sample selection, I was talking about these double solutions that are really difficult and make the inference very ill-conditioned. So what we essentially do is we remove about 30% of our galaxy sample actually that adheres or that shows these lack of identifiability problems. And the reason for that is we essentially trade off statistical, you know, we accept a slightly larger statistical error budget by removing these 30% of our galaxies. But what we gain is a better conditioning of the mapping, and also we remove the majority of galaxies that show very broad likelihoods. And we have tested a bunch of scenarios, and that has been, in terms of the risk assessment, be the best option here. In terms of the way we estimate, or the methodologies that we use to estimate galaxy redshifts, we also use basically two different approaches. So the basic picture that I've been giving you in the previous slides with this inverse problem essentially relates to a forward modeling approach. So the classical picture of modeling a spectral energy distribution that is redshifted through filter bands and compared with measurements. But you can also view this as a regression problem if you have available a training set. So what is often done in our field is we match our photometric data to spectroscopic observations when possible, where you have accurate redshifts, and we utilize this data set to train a direct mapping from the observed photometry to the redshift or other quantities of interest, for example, stellar mass or galaxy type. So this is essentially a machine learning approach. The disadvantage of this is you can only revert the arrow essentially if you have a training set available with both redshift and observed photometry. Okay, so I will just briefly go over, yeah, Jeff.
Yes, I wonder if you could go back 2 slides to where you talked about this. Yes. How can you be sure that this selection, I don't know if this is the only selection you did, but things like this are not going to lead to a bias in your results?
Yeah, so you need to include this selection in your forward modeling. So as any selection function, you need to include it. Otherwise, it will absolutely bias your results. You're absolutely right. So that's clear. So there are other more subtle things that can happen. For example, what we do is we have observations, and we cut out, redshifts that have, or galaxies that have these broad solutions, and that will definitely correlate with galaxy type. So the issue that we also tested is it could potentially also imprint the spatial signal because galaxy types differ in how they cluster on the sky. So if you remove, for example, certain galaxy types that show characteristic clustering, you might also bias or lead to a systematic signal in your galaxy clustering that needs to be modeled. But this was luckily not the case in our analysis, and we checked this extensively. But absolutely, you need to correct, or you need to mimic this selection in your forward modeling. Otherwise, you will bias your results. That's true.
Follow-up question on that. So if you, are there any cases where the galaxy types are determined only after the redshift is established, is fixed? Especially for large redshifts, is it possible that the galaxy type could be misidentified if the redshift is wrong?
Yes, so it's not a sequential process. So if you fit, so these SED models give you information of both galaxy type and redshift. So if you view this as a classical SED fitting problem, your model it contains both of these information. So it would jointly fit galaxy type and redshift. So you get a joint posterior of galaxy and redshift. But yes, absolutely, you can have if your model is bad, then your both quantities will be bad, or will be just wrong. And I should note that we are dealing here with very deep data. So the model is often wrong because we are at this point we are limited really by our understanding of galaxy evolution and galaxy physics. It's really difficult to get, for example, what we call complete template sets at the faint end of the color space. So if you plot these models for SEDs, there will be areas of color space that they won't cover. So model misidentification or misspecification is a huge issue for us. And that's one of the reasons why we need to essentially sometimes throw away data because we just cannot model it. And even in the case, I was mentioning this, spectroscopic surveys, they need a lot of exposure time to get spectra for these extremely faint galaxies. So your completeness of your spectroscopic calibration drops tremendously with increasing depth. So this all makes it extremely difficult to get to solutions that are of high quality. And yeah.
Thank you.
Okay. So I just wanted to very briefly go over the construction of the forward model. I use here a very simple model just to illustrate how that might look like. So on the right-hand side, you see, of course, it's a hierarchical model. And the reason why it's a hierarchical model is, of course, as we established earlier, you're interested in inferring the population distribution. So how does the distribution of a sample of galaxies looks like? You're not primarily interested in individual galaxies. So this naturally leads to a hierarchical specification. So what I show you here on the left in this equation is essentially a simple likelihood for parameters phi and z, which parameterize this sample redshift distribution. So essentially view the sample redshift distribution as a histogram. These histogram heights constitute parameters which are called here phi and z, and they would enter essentially as a prior to the redshift of each individual galaxy. And the second term here, which I call individual galaxy flux redshift likelihood, that would use this has the redshift of the individual galaxy as a parameter, and that's really the likelihood that you use to constrain the model. Then I have a marginalization of the individual galaxy redshifts Zi, because as I said, I'm not primarily interested in them, and you assume a product likelihood of all these measurements, which has its own assumptions. For example, the assumption of independence is technically not true, because you know, you could have, for example, if effects like blending. So if galaxies lie too close together, you have joint covariance between the flux measurements of different galaxies. But for the first order, we can often assume a product likelihood. So that kind of construction is again has the form of a classical inverse problem, and on the left-hand side, you essentially have a likelihood for the histogram heights of the sample redshift distribution. Okay, so and in the context of a regression analysis, if you have this the training set available, you can construct a direct mapping from the observed photometry to the redshift of galaxies, galaxy type, etc. And then it's often much easier to incorporate selection functions, because you can just incorporate it on the level of the training set. And the inference of these population distributions boils down to a marginalization. I briefly want to talk about the alternative data vector that we use in these kinds of scenarios. And we call this the cross-correlation method, but it's essentially two-point measurement, where we correlate binned-up spectroscopic information or spectroscopic data with accurate redshifts. This is shown here in this cartoon using these top hat functions with the sample redshift distribution shown in black, where you do not have the redshift information available. So black would in this case be an HSC survey, and red would, for instance, be DESI, yeah, as a sample. And what you construct is essentially a two-point function measurement between the spectroscopic survey, where you know the redshift quite well, and the photometric survey, where you would like to determine, you know, the redshift of a sample of galaxies. And the signal that you measure using these two-point functions is proportional to the redshift distribution of the unknown sample, so of the photometric sample. And there are, of course, huge degeneracies in galaxy-like matter bias, as well as cosmological dependence due to the dark matter field. But this is one of the alternative ways how you can determine essentially the sample redshift distribution simply by cross-correlating with these kinds of reference samples where you know the redshift quite well. So in our case, and I briefly go over this, we're actually using, we do not have very good spectroscopic surveys with accurate redshifts that we can use. So what we use is a subsample of galaxies where we have good enough redshift measurements, but that are still subject to some error. So we use what's called the luminous red galaxy sample, so a particular galaxy type where the photometric error is quite low. And I just mentioned this. We have redshift error of 0.03, which is an order or a factor of 3 lower than for other galaxy types. So what we do essentially is self-calibration. So we perform two-point function measurements between subsamples of galaxies and try to exploit redshift information using these cross correlations. Now, the issue, of course, is you need a marginalization scheme for the redshift of these kinds of reference samples. What we use is we developed an importance sampling scheme where you essentially would generate new catalogs of these reference samples within this redshift error, and can marginalize over the redshift error using importance sampling and with a reasonable proposal distribution. Okay, so I want to briefly walk you through the basic results we obtain in the context of HSC. and how that looks like. So the combination of the inference of the photometry of galaxies, as well as incorporating these spatial cross correlations, forms a joint likelihood. And we use this joint likelihood to obtain our final results. And I show you the different components of this likelihood here in these four tomographic bins for the case of HSC. So what you see here in gray is what I call photo-Z. This is the information you have on the sample redshift distribution only using the photometry. So this is essentially the output we get from our deconvolution inference. And then on top of this, yes, Jeff?
Sorry, I didn't want to interrupt the thread, but can you say what these error bars are?
Yeah.
It's the classic case where the scatter of the points is much less than the size of the error bars. So are those including systematic errors or something? Or
yeah, so there are a couple of things to note here. Yeah, they include systematic errors. First point. Second point, they're highly correlated. So both of these factor in, but you're absolutely right. They include systematic errors. That's why they are larger. So you wouldn't expect them to they are overestimated essentially. Yeah, but we know this. Yeah. And there are two different types of points that you see here. So the first one is these black points, which are these come from this cross correlation data vector. And the second is this smaller blue point, and the smaller blue point is the standard deviation of the mean clustering redshift, or the inference obtained on the different importance sampling realizations of the reference sample. So how much does this measurement change when you have different realizations of the reference sample? And they have to be small, because otherwise our convergence of the importance sampling scheme would not be good. So this is essentially showing you that the importance sampling is relatively well behaved. And what you see in red is you have this joint the joint constraint using both the measurement of these cross correlations as well as of the photometry. And I should make one point that's maybe interesting to you. So you cannot just use standard MCMC sampling in these cases. The reason for that is because you are actually inferring probability distributions. So if you would parameterize them as a histogram and normalize these histogram heights accordingly, you would know that you can normalize them to be unity. So the issue that you are facing is when you perform inference in these models, if you use standard MCMC sampling techniques, you could get, for example, negative. Your error bar would extend to negative values, yeah, which is not correct, because you're dealing here with purely probability distributions that you would like to infer. So we actually use specific inference techniques and MCMC techniques that work on these constraint spaces, because there's a constraint there that all the histogram heights have to sum to unity. So you have to incorporate that in your MCMC sampling scheme. And so this is another thing that I think is useful to mention here. And if you're interested in that, I can expand on how we do this exactly. But what you see here is that the joint constraint, which is shown here in the red, is much lower than what you would get with each individual method alone. And that is essentially what we use for our cosmology in the end. Similarly, you see that at the highest redshift bin, we have huge issues with our calibration. So we have, first of all, we lose a lot of data because we need to cut out a lot of galaxies due to the aforementioned issues with our modeling. You also do not have reference samples that you can cross-correlate against very easily, because these samples are at higher redshift and quite faint, and that's why we need to make sure in our analysis that you give a very conservative error budget on the highest tomographic bin error distribution. Okay, so this is the final slide that illustrates the results we obtain. So what you see here is a quantity of interest that we often use in recleansing and large-scale structure measurements. That is what we call a posterior tomographic mean. So for our purpose, one of the most important parameters that we actually care about is how much does the mean, so the average redshift of the sample of galaxies change, yeah, within the errors. So if you view these contours as distributions over probability distributions, and you draw multiple realizations of them, and on each realization you calculate the mean of that, what we call tomographic bin, you would get a distribution over the mean. And this is shown here in these 4 different panels. And we use that primarily to marginalize over the redshift uncertainty in our cosmological analysis. And what you see here is in the lowest tomographic bin, we still have a significant amount of systematics, whereas the second and the third, where our systematics are lower, because our modeling of the SEDs is, for example, much better, and we have more consistency. And at the highest tomographic redshift bin, we unfortunately do not have alternative ways to cross-correlate. I also quote some of the values that we assign. What you see here in the last column is that actually we almost are conservative to a factor of 3 in our error distribution for each tomographic mean because of the aforementioned issues in calibration and model misspecification. So that's that concludes my talk. Thank you so much for your attention, and I'm very happy if you have any questions. I hopefully can answer them.
Hey, thanks, Markus. It's very detailed and complicated subject here. So any questions from anybody here? I mean, we did ask several questions along the way.
Yeah, I have a question, probably some very basic trivial question for you. So first of all, how many sources or galaxies you have in each bin? And if you're looking at the population of sources, does this because you would have a spread in the redshift of that population of sources. So what does it mean? I mean, I'm not using this type of studies. So you said you're interested in the mean, but there is also a spread, right? And the spread could be due to the intrinsic spread in the redshift of the galaxies, or due to the errors, right? So what are these two things? Yeah.
So first of all, regarding the amount of galaxies you have, because that's super relevant actually as a question. 10 million in this, approximately on average, 10 million galaxies in each of these tomographic bins. So 10 million galaxies is still manageable computationally, but if you think about running complicated MCMC chains, and your likelihood needs to be evaluated on 10 million galaxies, your cluster has something to do. So that's a very important question. LSST, yeah, we have 10 to the 10 galaxies. That's a huge computational issue for us. Doing these kinds of inferences. Yeah. It's actually we do not actually know how to solve it at the moment. Yeah. So probably something stochastic likelihood evaluation or something like this would be in order. But this is the first point. Your second point. So you are absolutely right in saying that when we concentrate on the mean, yeah, and on the uncertainty in the mean, this is a huge oversimplification. The reason why we do this is because so we know that this would affect, or this can bias our inferences, our cosmological contours. It will bias them because we have an oversimplistic model. Yeah, so the spread, so the error in the standard deviation will affect our modeling. But at the current error that we have in stage 3 surveys, it is something that is not dominant. So what we say is, we accept a systematic error because we are using a simplified model for the error due to computation considerations. Moving forward to LSST, where we have smaller error bars, this model misspecification or this oversimplification is something we cannot do anymore. Mm-hmm. And then we need to think about including higher order moments or actually marginalizing over the full distribution also in our cosmological analysis. So, but again, it's a computational consideration. One example I can tell you is for the actual cosmological pipeline that we use for these recleansing measurements and large-scale structure measurements. You typically do not have gradients for the likelihood. This just one example. So a lot of efficient inference techniques, HMC sampling, these kinds of things, they don't work. And the individual evaluation of the likelihood can also be quite costly. So computational considerations are a huge factor here.
All right. Yeah, thanks.
Jeff has a question.
Yes. Yeah. Thanks for this nice talk. And one of the things that I think this kind of analysis could be useful for is in designing the experiments, so to speak. What I have in mind is that I'm a little familiar with how for example, the band passes are chosen in experiments like this and in campaigns, Redshift surveys, and so on. But in principle, this kind of analysis could be used to optimize the choice of the band passes and maybe other instrument design techniques, which I think is a term that Tom Laredo has promoted. But do you know of any instances like that where this kind of analysis has been used in designing of the survey from the beginning?
No. So there's a temporal factor here, right? So these kinds of surveys that have been proposed over 10 years ago, yeah. And the way we perform Redshift inference has evolved quite drastically in the last five years. So there has been some optimization done in terms of the size of these optical filter bands, and slightly modifying the position to avoid these degeneracies. But so this analysis has been not so the full analysis where you also talk about this is an inverse problem. We want to get a condition number in our operator that's actually manageable to the resolution where we need it to be, which is, I think, what would be the actual correct way to design these kinds of surveys, as you mentioned. That hasn't been really done, but there has been in the optical, there has been some optimization done just to think about to reduce these lack of identifiability problems. But what you see here is, and I think that's super relevant to your point. So the optical will often have these issues that you cannot distinguish between two different galaxies lying at different redshifts. But if you go to the near infrared on the right-hand side, you can often very well break these degeneracies. And this tells you something about the role, I think, this is my personal opinion, about these optical surveys in the context of cosmology going further. I do think that due to these, due to these limitations, specifically on distinguishing different galaxy types lying at different redshifts, that is a fundamental issue actually for the way we perform science. We need to think about joint analysis with other survey types, because this will help us tremendously, I think, in this area, and specifically combining it with survey types that have narrower filters. Yeah, for example, what we do is we do some preliminary analysis calibration using Cosmos. But also looking at the near infrared, whether we can incorporate data on that end.
So this is I have a follow-up question for Jeff actually. What sort of process were you thinking of, Jeff, in terms of how to do such a exercise as figuring out what the bands should be?
Well, I guess I didn't really have anything specific in mind, other than just generally. I mean, with this kind of formalism, you could imagine doing a simulation study where you simulate the whole experiment with different band passes in terms of their locations and widths and shapes even, and try to optimize the throughput of the survey in terms of accuracy of the photometric redshifts, individual and distribution wise, optimized with respect to the parameters defining the band passes. It seems to me that that kind of a study is possible, and might be very useful, because the choices of the bands they're made in a principled way, but they're not explicitly optimizations of anything. As far as I know, there's no explicit numerical optimization studies. I could be wrong about that.
I mean, yeah, and I guess the one shows the big problem, of course, is that because people want to have the same bands in all surveys, so you can't really change them too much, other than maybe adding some extra bits.
I'm not sure that's true. That's a good question, but I assume that, I mean, you're talking about hardware, basically, you know,
Yeah.
And I think people tend to, the choices are also informed by practical things like expense of the filters and, you know, whatever. So I have a feeling that people don't try to have identical band passes in different surveys. Maybe someone else knows more about that than I do, but.
I mean, yeah, you're right. I mean, they wouldn't be exactly identical. There's always variations. But yeah. Anyway, Kate, so go ahead.
Oh, if I could ask another question, if there are other questions, I can wait. But
Casey has had his hand up for a while, so maybe you can ask and then can come back.
Thanks. I was a little confused about the plot, which is on the upper right. Mm-hmm. So you have 4 different distributions, those curves. And I would assume that's the your estimated redshift distribution within tomographic bins, 4 different bins. Is that right?
That's correct.
So how did you define those bins?
Yeah, so they have been. Yeah. Okay,
well, so, I mean, so it looks to me that well, maybe this is my misunderstanding, but it sounds a little circular to me that you have divided up the galaxy into redshift bins, but you don't even know what the redshift is. So how are you even doing that?
Yeah. So that's a good question. So you are doing this based on essentially maximizing your info. So you would like to maximize essentially the information, the redshift information that you can exploit to constrain the growth function, right? So you would like to, because we are using 2-point function measurements and splitting up the sample as a function of redshift and defining 2-point statistics on each of these samples, and including cross correlation, just maximizes, gives us more information on the redshift dependent of the growth function. So that's the first point. And in terms of statistical methodology, how you do this is you are defining a selection function based on the likelihood of individual galaxies, and you need to include this selection function in your forward modeling. Yeah. So you are saying I have a selection function to put these galaxies in these different bins, and you essentially forward model the selection function in your in true space. Yeah. So, but because you cannot do it perfectly, you get these tails. So you do not have a perfect separation, but because the redshift is uncertain, you will get incomplete separation, but you need to incorporate this essentially as a selection function in your forward modeling.
Sorry, but can you clarify, what is the selection function a function of?
Of the, you could say it's, roughly speaking, it's of the mode, so of the maximum likelihood estimate.
Of what?
Of the individual galaxy redshift.
Okay, so you have a method, so you don't have spectroscopic redshifts. So you
Yes.
are estimating individual photometric redshifts from
That's
the
correct.
brightnesses and colors.
Then I get the maximum likelihood estimate.
Yes.
And then you define the selection function based on this maximum likelihood estimate.
Okay, so you have a maximum likelihood point estimate of the redshift of
That's
these
correct.
galaxies. Then
Yeah.
you sort your 10 million galaxies into 4 bins based
That's
on
correct.
that MLE.
Yeah.
And then what you're doing here is estimating the distribution of the photo Z within the bin.
Within the bin, yes. So you have a maximum likelihood estimate for each individual galaxy. You use that to chunk these galaxies up into 4 containers, right?
Okay.
And then you perform your sample redshift inference within these 4 containers. This gives you these four bins, but you have applied a selection function, right? Because you select these galaxies into these 4 containers. So you modify your likelihood to incorporate the fact that you have selected your galaxies based on the maximum likelihood estimate. You need to truncate your likelihood, because otherwise your inference would be biased because you do not incorporate the selection function. It's the same issue if you have regression, right? If you have a regression problem and you are selecting on the target variable, on the dependent variable, yeah. Mm-hmm. So you need to modify your likelihood for this regression. Otherwise, you get biases.
Well, yeah,
that's obviously, but that's what we do here.
Okay.
Can I ask a follow-up question? So,
sure,
I mean, you didn't. Oh, sorry. I'm just gonna assume that I had permission. But so, I mean, you didn't describe your hierarchical Bayesian model in great detail. But suppose in a bin, you know, hierarchical Bayesian models usually implement some kind of shrinkage, shrinkage toward the center. So, you know, in each of those bins, you see a peak distribution near the center of the bin. And I was wondering how much of that is due to shrinkage rather than the actual distribution of galaxies within your bin. Yeah,
so shrinkage is a problem, actually, because so on the left-hand side, you see that within a bin even, right, you have vastly different errors. Yeah, so that can actually lead to a bias if you just use. If it's just because you're assuming the same prior distribution over all different galaxy types, so you're not necessarily conditioning on the galaxy type that will determine, you know, how big these error models are, or how broad the error will be, and that can actually lead, because of shrinkage, to a bias in the recovery. But this bias is often, we have tested this. It is subdominant to other sources of systematic. It's not that big, but there is shrinkage going on because you know, ideally you have to make sure that the error model is comparable, you know, within each container that you're using in your tomographic in your hierarchical model, in order to avoid that the likelihood essentially dominated, or the inference is dominated by galaxies that have quite narrow error bars, or quite narrow likelihoods, and that can essentially lead to shrinkage where broad galaxies the information from broad galaxies essentially downweighted. Yeah, so that's a factor, and but at our current error bars, it's subdominant.
Okay, thank you.
Yeah, but for LSST, we need to take this into account. So we need to add the conditioning based on the spatial position of galaxies, based on galaxy type, other parameters, just to make sure that that we reduce this shrinkage issue. Yeah.
So okay, maybe Jeff should ask he's been waiting.
Yes, thanks. These questions you were just discussing are perfect introductions to what I want to ask, and has to do with use of binning in general.
Mm-hmm.
Some of you know I've been on an anti-binning campaign for a while, and in principle, the cumulative distribution can be dealt with in a completely, in sort of effectively bin-free way. And I always wonder why this kind of analysis can't be carried out in a much better way, avoiding the loss of information and dependence on bin choices using cumulative distributions instead of differential distributions.
Yeah, so I can maybe try to answer this. So I think it's mainly practical considerations and historical considerations. So just for illustration purposes, so what we do is, so this is an input essentially to a cosmological inference that uses angular correlation functions. Angular correlation functions are essentially you project your 2-point function that's defined in 3D. With 3D, I mean right ascension, declination, redshift. Yeah, you're projecting it down to 2D with in the projection kernel is exactly these redshift sample redshift distributions. So that's why so the actual modeling quantity is the probability density function in tomographic bins. So the binning is included in the way we define our cosmological likelihood. So that's one of the reasons why we are using this binning, and not because you could deconvolve this density field in 3D without loss of any information due to binning. And that actually improves your cosmological parameter constraints, because you are not binning. So you're not losing line of sight information. So this is just essentially you could view this maybe as a Cox process, right? And you're deconvolving the line of sight distribution. You could do this in 3D as well as you can do this in 2D. It's just because the other working groups, they use projected correlation functions that we perform this inference in a bin fashion. But I completely agree with you.
But in principle, that I mean, it's an example where you're interfacing with other scientific projects or viewpoints, and so you would all have to adopt a bin-free approach in order to be able to work together. I think I'm summarizing what you're saying, but in principle, the kind of spatial analysis you're talking about can be also done in a essentially bin-free way using cumulative distributions.
Yes. Yeah. So I agree with you. It's just
So are there any young students on this call who want to embark on a project of doing all of this stuff in a bin-free way? I think that would be great.
Yeah, I mean there are efforts that do this, and I'm leading one of the projects with this. I mean, the student is leading the project. I'm just supervising it. That does this in the context of LSST, but it's not. So there are efforts to do this, but it is not at a stage, I think, that's production ready. There are also computational considerations that factor into this. So if you do it in a non-free fashion without binning, so just deconvolving the 3D density field, it's typically in terms of the inference, it's computationally more a little bit heavier. So that's something that we are still that needs to be figured out. But I agree with you; it would be the better, more principled way. Yeah.
Okay. Any other questions? We are over time, though of course not technically, but still well past noon here. So any other questions? And if not, let me ask you a couple of quick questions, Markus. So one is, I must admit that I don't entirely understand the tomographic binning things. What are you exactly achieving from this?
Yeah, so you're achieving essentially adding redshift information in your cosmological likelihood. So what we do here is practically this enters a cosmological analysis that measures the 2-point function in each of these tomographic bins. Right. Think about it as just galaxy clustering in each of these tomographic bins. Mm-hmm. And then you write down a joint likelihood of these 2-point function measurements in each of these tomographic bins. And what that gives you is it gives you redshift information on the growth of structure. Because you have, if you, for instance, would compare the this without binning, so just the full, using the full sample redshift distribution and just do one autocorrelation function measurement, yeah, of this full sample. And again, it's an angular correlation function, so you're projecting it down to 2D. You're losing a lot of the redshift information, right, of the growth of structure. So it's a binning thing. So we are essentially approximating. Mm-hmm.
So so my question is actually, I mean, how does that what does it tell you about the cosmology, or what is the connection to the physics such as there is in cosmology?
Yeah,
I should say that.
So what we're actually interested in is constraining the growth function. The growth function has a redshift dependence, and we would like to probe this redshift dependence because the redshift dependence is something that we can use to distinguish different dark energy models, for example. Yeah. So we need to include this redshift dependence in our constraint, or we need to maximize the redshift information we get on the growth function in our cosmological measurement.
Okay. So you're effectively trying to figure out portions where this growth function has maximum change.
Yeah. Yeah. Maybe this is a good picture. Think about picture the growth function.
Yeah.
And now we are binning up this growth function in these tomographic bins.
Yeah.
And you are getting one error bar on this growth function from each angular correlation function measurement in these bins.
Okay. Okay.
If you have just one angular correlation function measurement over the full sample, you get one error. So you get one measurement. Yeah. But it's better to have more measurements. So you can trace the redshift dependence of the growth function using this tomography.
Got it.
So that's the idea. So picture growth function with little points. Yeah.
Okay. All right. Thank you. We are shedding viewers, the audience, so we should probably wrap it down unless there are any final questions. If not, thank you again, Markus. This was a fascinating talk. I'll try to put this, get this thing on our YouTube channel as soon as possible. So hopefully you'll probably get questions from the people who will watch this off later.
Thank you so much.
So, let me turn recording off.